All right, let's work on an example here that's got a couple of different coefficients of friction. So it says we have a 1,500 kilogram car heading west, which slams on its brakes. So let's move that out into the big space here. We'll draw our flat surface. Here's our car. Mass equals 1,500 kilograms. It's going to be a force of gravity of 15,000 newtons, and we won't be able to get this to scale. Now that thing's heading west. We're going to have a normal force that balances it out. So the normal force is also 15,000 newtons because we're on a flat surface. And then if the car was heading west, we'll assume for the purposes of this that east is right and west is left. So there's no force accelerating the car anymore forwards, but there is a force reducing it, and that's the force of friction. And we can draw in the force of friction, but we don't know what it is just yet. But it says, so if we just were asked to draw the diagram, this would be it. And that's all the information we could put for force of friction if that's what they were asking for. So then it says, what would the frictional force be to stop the car on a sunny day? So let's go to one of our equations here, that the force of friction is equal to mu times the normal force. And in this case, we have 2 mu's, but for a sunny day, we can assume that that's for rubber and dry asphalt. So that's 0.9. So we can go ahead and substitute in here. We've got the coefficient of friction, and we have the normal force. So it's going to be 0.9 times 15,000 newtons. So try to place that where you guys can see the calculator actually. And 15,000 times 0.9 gives me 13,500 newtons. So for a dry day, and we're going to do a wet one here in a second, so I'm not going to fill this in, we'd have 13,500 newtons of friction force working to stop that.